Welcome back to the Deep Dive, where we take complex industry documents, engineering requirements, and deep research and distill them into the essential knowledge you need to be well-informed. Today, we're not focusing on the luxury end of the automotive spectrum or the latest billion-dollar self-driving software suite. We are diving into a silent revolution happening on city streets globally. Microelectric vehicles, or MEVs.
It's a fascinating space. We're talking about the LSEV, the L6E, and the L7E market segment. And historically, this space was, well, it was kind of dismissed, seen as slow, low-tech, and frankly, a bit unsafe.
Right, the technology was almost an afterthought.
It really was. This market relied on simple industrial-grade controllers. I mean, the kind you might literally find driving a golf cart or a basic forklift.
So they were designed for a simple duty cycle, not for functional safety.
Precisely. That distinction is so critical. These vehicles were rudimentary, often lacking proper diagnostics, any real functional safety mechanisms, and certainly no integration with modern networking standards.
But the sources we've analyzed show a profound shift is underway. I mean, you look at the immense market success of platforms like the Wuling Hongguang Mini EV.
Total game changer.
It proved there is this explosive demand for affordable, quality micromobility. And, when that kind of market opportunity opens up, regulators start paying very close attention.
Absolutely.
Wow.
We are seeing a mandated paradigm shift.
Right.
The regulatory upgrades, and they're mandatory, from the demanding EU regulation 168/2013 to the new, very stringent China GB standards. These are the true catalysts here.
So they're forcing the industry's hand.
They are. They're forcing every manufacturer in this high-volume space to ditch the simple switch logic and the bare metal programming of the past.
And that leads us directly to our mission statement for this deep dive. Today, we are synthesizing what a top-tier global automotive engineering consultancy would produce.
A detailed vehicle control unit engineering requirement specification, an SOR.
Exactly. We're defining the technical mandate to transform the VCU from what it used to be, just a simple motor drive signal source, into what the global market now demands, a sophisticated powertrain domain controller.
And our core mission here is to really establish the non-negotiable legal and technical boundaries you need for a global market entry. If you want to sell in the EU, the US, Japan, or China, this VCU absolutely cannot be successful without meeting ISO 26262 functional safety standards, supporting the AUTOSAR framework, and of course, passing that rigorous ISO 16750 environmental validation.
So these mandates aren't suggestions, they're the price of admission.
They are the entry ticket, period.
So we are not just talking about building a better component, we're talking about building a compliance structure, a technical fortress, really, to ensure product integrity, brand safety, and market credibility. That's why we're starting our deep dive by tackling the legal boundaries that directly dictate the VCU's fundamental design. Because, really, the law informs the chip, not the other way around.
When a systems engineer begins a global MEV platform design, you simply cannot start with the microprocessor or the cost target. You have to start with the law. These disparate global regulations, they are the primary inputs that dictate the VCU's control strategies, its diagnostics, its safety mechanisms. The penalties for non-compliance are absolute. The vehicle just cannot be sold.
It sounds like a masterclass in regulatory divergence. So let's start with one of the most prescriptive environments out there, the European Union.
Right. The EU framework, which is Regulation 168/2013, provides a very, very granular classification system for these quadricycles. This is where we define the technical walls.
Okay, so detail those classifications for us. What are the key numerical constraints we're looking at?
So you have the L6E, which is the light quadricycle. It's strictly limited. You're looking at an unladen mass below 425 kilograms, a maximum speed under 45 kilometers per hour, and a power output capped at 6 kilowatts.
And the L7E.
That's the heavier counterpart. It gets a bit more leeway. An unladen mass limit under 450 kilograms and a much higher power allowance, all the way up to 15 kilowatts.
So right away, the VCU has a massive engineering challenge. The manufacturer wants to use the exact same hardware across their product line for economy of scale.
Of course.
But that one VCU needs to legally manage two completely different performance envelopes.
Exactly. This is the parameterization requirement. The VCU architecture has to be intrinsically flexible. The core hardware and the underlying basic software, the BSW, they must be identical.
Yeah.
But they have to be configurable at the end of line phase, the EOL phase.
So right as it rolls off the assembly line.
Precisely. If a vehicle is destined to be an L6E, the software must be flashed with a specific parameter set that rigorously enforces that 45-kilometer cutoff. If it's an L7E, well, those parameters are released.
That seems simple enough on the surface, just a software gate. But it also sounds highly vulnerable to tampering, doesn't it? Someone buys an L6E, they could try to illegally flash it with L7E parameters to get more speed.
And that's exactly why the critical anti-tampering design is a type approval requirement in the EU. It's why the VCU needs that advanced engineering. The VCU cannot rely on just one sensor to enforce that speed limit.
Because, as you said, a single wheel speed sensor could be easily disconnected or even spoofed.
Right. So what's the specific redundancy required to satisfy the regulators? The VCU must continuously cross-check two disparate data sources. First, the motor resolver speed, which is derived directly from the motor shaft itself.
Okay. And the second?
The ABS wheel speed signals, which measure the actual rotation of the wheels on the road. Now, if the VCU detects a significant illogical discrepancy, let's say the motor is spinning fast enough for 60 kilometers, but the ABS sensors are reporting only 40.
Or one just goes silent.
Or worse, one goes completely silent. The VCU have to assume tampering or a fault.
And its reaction in that safety condition has to be immediate.
It must fail safe. The VCU can't just ignore it or default to no limit. It is legally mandated to enter a crippled speed, a limp mode. This design ensures compliance and safety, even if a user tries to fool the system.
That necessity for cross-checking sensors and really anticipating illegal modification pushes us deep into functional safety territory, doesn't it? Even if full ISO 26262 isn't formally required for these L-category vehicles.
It absolutely does. Article 22 of that regulation states the VCU must maintain functional safety throughout its entire normal lifespan. Now, that is a profound engineering mandate.
A normal lifespan. What does that mean in practice?
It forces the VCU design to account for component degradation over years of use, not just a sudden catastrophic fault.
So lifetime monitoring, that implies far more than just error checking. Can you give us a concrete example of this life cycle aging monitoring the VCU has to perform?
Sure. Think about the accelerator pedal. For safety redundancy, it uses dual-path signals, usually two separate potentiometers giving 0.5-volt signals.
Okay.
After 5 years and tens of thousands of cycles, the carbon track inside those potentiometers, it starts to wear down. This wear causes subtle resistance changes and signal drift. So the two signals, path A and path B, which should track perfectly, begin to diverge just slightly.
So the VCU has to detect that tiny drift before the driver even notices there's a problem.
Precisely. The VCU must incorporate an automotive-grade analog-to-digital converter, an ADC, with extremely high precision and a high diagnostic coverage factor. It needs continuous monitoring algorithms to identify when the inconsistency between path A and path B exceeds a calibrated threshold, a clear sign of wear, and then enter a safety state before that wear causes an unsafe change in vehicle response.
That requires some serious, robust hardware and software design from the get-go.
No question.
Okay, shifting to the U.S. market. We're dealing with the Federal Motor Vehicle Safety Standard 500 for low-speed vehicles, or LSVs. Compared to the EU's two-tiered system, the U.S. rule seems simpler, but I suspect the engineering challenge is just as acute.
The U.S. system is simpler in classification, yes, but it is fiercely strict on its single constraint. The absolute red line is 25 miles per hour, about 40 kilometers. FMVSS 500 mandates that the LSV's maximum attainable speed cannot exceed that limit under any circumstances.
Any circumstances. And this is where the VCU's control logic has to be significantly different from the EU's, especially when you factor in kinetic energy and gravity.
That's the key challenge. If the vehicle is coasting down a long, steep hill, gravity can easily push it past 25 miles per hour. The VCU can't just cut power. It has to actively intervene. This is the requirement for downhill overspeed control logic.
Wait, actively intervene. You mean actively braking, using the motor, essentially turning it into a generator to limit speed?
Correct. This is where the VCU becomes a real-time dynamic modeler. It needs to fuse sensor data speed sensors plus an integrated accelerometer to calculate the vehicle's acceleration and effectively estimate the slope.
So it's calculating the forces acting on the vehicle.
In real time. And if the system calculates that the vehicle is going to exceed 25 miles per hour, the VCU must actively command an increase in motor regenerative braking torque.
That requires some pretty complex dynamic software modeling, doesn't it? This isn't just a simple lookup table saying if speed is over 25, apply 10% regen.
It is far more sophisticated. If you apply regen too aggressively, you risk instability, especially in these micro EVs with shorter wheelbases and smaller tires. The VCU has to calculate the maximum safe regenerative torque possible to scrub off speed while ensuring stability. It has to act as a proportional active speed governor. That 25 mile per hour ceiling is unbreachable.
That is a huge burden on the VCU's processing power. Now, the sources also highlight that the U.S. has relaxed the gross vehicle weight rating, the GVWR, allowing LSVs up to 3,000 pounds.
About 1,361 kilograms, yeah.
This opens the door for microelectric delivery vans, and that introduces a completely different power management problem.
It's a huge commercial opportunity, but a major VCU challenge. A delivery van's load can fluctuate dramatically. When a van is fully loaded, say 1,300 kilograms, and it starts climbing a steep ramp, the motor and inverter are demanding peak current. The VCU has to manage that intelligently.
So the VCU needs to know its load dynamically.
Yes. The VCU's torque map has to incorporate advanced load estimation algorithms. It can infer the current load by observing the torque required to maintain a constant speed or the current draw needed for a certain acceleration. This dynamic load estimate lets the VCU adjust the motor current limits in real time.
And why is that dynamic adjustment so critical, specifically on hills?
Two big reasons, both related to safety and durability. First, motor and inverter protection. If a motor is straining under max load for too long, it will rapidly overheat, potentially causing permanent damage. The VCU has to dynamically derate the available current to prevent thermal runaway.
Okay, that makes sense. And the second reason?
Anti-rollback and startup torque. If that fully loaded van stops on a steep slope, the VCU has to deliver enough instantaneous starting torque to prevent a dangerous rollback before the driver even touches the accelerator. The load estimate ensures the current delivered is just right, not too little, causing a roll, and not too much, causing an overheat.
Let's move to China. Their regulatory environment has matured so rapidly, moving from just focusing on volume to enforcing some of the most technologically demanding standards globally.
You're right. Compliance with the new Gobiao standards is non-negotiable for any modern MEV platform, and they're setting global benchmarks, particularly in battery safety.
The new battery standard, GB 38031-2025, which becomes mandatory in 2026, sets a standard of no fire, no explosion during battery thermal runaway. That's a zero-tolerance policy that has to impact the VCU even when the vehicle is supposedly parked and off.
It fundamentally redefines the VCU's state management. Traditionally, when you shut down an EV, the VCU goes into a deep sleep to conserve the 12-volt battery. Under this new GB standard, that approach is just too risky. The VCU can't fully power down. It must enter a low-power monitoring mode.
That sounds like an electrical engineering nightmare. How do you keep critical safety components running while hitting near-zero consumption targets?
It is a massive challenge. The target is a static current draw of less than 100 microamperes, 100 away. You are engineering a perpetual guardian state. In this low-power state, the VCU has to continuously monitor hardwired wake-up signals from the battery management system, the BMS.
The BMS is still the primary sensor on the pack's health.
Always. So if the BMS detects a problem like a pressure spike or a rapid temperature gradient that precedes a thermal event, what does the VCU do?
It has to react instantly.
The BMS triggers that hardwired wake-up. The VCU must execute an emergency protocol in milliseconds. And this isn't for the driver. It's for alerting the public and emergency services. It triggers the full vehicle alarm horn, flashers, and immediately sends an SOS signal via the T-box. This has to happen even hours after the vehicle has been left unattended.
It transforms the VCU into a key part of the vehicle's passive fire suppression and emergency notification system.
It does. And that requirement alone, managing a hyper-low power state and an instantaneous high-priority wake-up, is a monumental shift. And beyond safety, China is also enforcing a new mandatory energy consumption standard starting in 2026.
They're tightening the noose on efficiency.
Absolutely. If you're building a heavy EV, for example, you might be capped at 15.1 kilowatt hours per 100 kilometers. This puts immense pressure on the VCU to optimize everything, not just the drive motor.
So how does the VCU software get that granular about energy efficiency?
It requires highly sophisticated energy management strategies. The VCU must implement on-demand control for every high-voltage accessory. The DC-DC converter, the AC compressor, the PTC heater, you name it.
So in an eco mode, for example.
Exactly. In eco mode, the VCU won't just soften the accelerator pedal. It will actively calculate and limit the maximum power draw of the AC compressor, maybe reducing its duty cycle from 100% down to 75%. It has to optimize coasting region efficiency to harvest every last watt. It's an algorithm driven by the necessity of hitting a government number.
Our final regulatory stop is Japan, where the ultra-compact mobility focus is heavily informed by demographics, specifically safety aids for an aging driver population.
Yes, the Japanese market really emphasizes accident prevention, particularly for common human errors. This translates into a strong market suggestion, and it's rapidly becoming a requirement. for pedal misapplication suppression.
This system addresses that notorious mistake of drivers confusing the accelerator and the brake, leading to rapid, unintended acceleration. How does the VCU manage to override the driver's intent safely?
It's a classic case of sensor fusion and logical overriding. The VCU has to integrate inputs from the pedal position and inputs from the vehicle's environment sensors, ultrasonic radar, or cameras. The logic is both behavioral and contextual.
Can you walk us through the VCU's thought process on that one?
Sure, imagine the vehicle is static or moving very slowly in a parking lot. The VCU detects a massive rapid jump in the accelerator signal, 0% to 100% instantly. But at the same time, the radar detects a large obstacle, like a wall, directly ahead. The VCU identifies a high probability of misapplication.
So it overrides the driver.
It has to. It must override the driver demand, dramatically limit the output torque to prevent a surge, and trigger an immediate warning alarm. This requirement just highlights how the VCU, even in a so-called micro-EV, is integrating functions that were once reserved for high-end ADS systems.
We've built the regulatory map, that technical iron cage of constraints. Now let's move to the physical system design. The choice between a 48-volt low voltage and a high-voltage architecture seems like the first, most critical strategic decision.
It is. It dictates the entire component selection and safety overhead. This choice determines, I'd say, 90% of your safety protocol documentation and hardware costs. The VCU's responsibilities fundamentally change based on whether you're below or above that critical 60-volt DC threshold.
Let's start with architecture A. The 48-volt low-voltage system, we see it in vehicles like the Citroën Ami. It's often chosen for pure cost optimization and simplicity. What are the VCU's advantages here?
The primary advantage is that the system voltage is always below 60 VDC, which makes it touch-safe. This drastically simplifies the safety architecture. As a systems engineer, I immediately see massive bill of materials, or BOM, savings.
And where do those specific VCU cost savings come from?
Well, first, functional safety requirements are eased. You don't need the highly complex high-voltage interlock loop or HVIL monitoring circuits. You completely eliminate the need for expensive insulation monitoring modules. And crucially, you can use cheaper, standard automotive-grade connectors and harnesses, avoiding those heavy, expensive, shielded high-voltage connectors.
That sounds great for a city car. However, 48-volt systems, to deliver meaningful power like 6 kilowatts, they require massive currents. We're talking 150 amps or more. Doesn't that create a new set of fire risks the VCU has to manage?
It absolutely does. It switches the focus from voltage safety to current safety. High current means the VCU has to implement obsessive thermal diagnostics. It needs to monitor harness temperature, terminal temperature, and contact resistance very, very closely.
Why the focus on contact resistance specifically?
Because if a connector degrades over time from vibration or corrosion, that tiny increase in resistance across the contact point generates immense heat due to the high current. P equals I squared R. The VCU has to be designed to detect this localized overheating signature and immediately derate power before the heat causes melting or fire.
So this architecture is really best suited for the L6C category, where speed is low and minimizing cost is everything.
Exactly. But once you step up to performance, the L70 category, or vehicles like the Willing Mini EV running at 100V to 150V, you have to adopt architecture B high voltage.
And the moment you cross 60 volts, the VCU immediately inherits the role of the primary high voltage safety manager, right? Its job moves from controlling torque to controlling life-critical electrical safety.
Precisely. And this requires 3 complex mandatory sequences the VCU must execute flawlessly and redundantly.
Let's detail the first one, HVIL monitoring.
Okay, the high-voltage interlock loop is the physical safety chain. The VCU generates a low-voltage signal pulse, typically 12V or 5V. This signal has to pass in series through a physical wiring loop that connects every single high-voltage component, the battery pack, the motor, the inverter, any heaters or chargers.
And if that loop breaks, say in a crash...
If the loop breaks, a service plug is removed, a cable is sheared, the return signal to the VCU is lost. And the VCU must recognize that break and cut the main contactor, the big relay disconnecting the battery, in under 200 milliseconds.
Yeah.
This is a hard real-time safety function.
Okay, that's critical. Next, the VCU has to monitor for potential leakage or shorts, the insulation monitoring duty.
This protects against shock risk and short circuits. The VCU communicates with the BMS via CAN to read the insulation resistance value between the high-voltage bus and the vehicle chassis. If that resistance drops below the threshold, 500 ohms per volt is the legal minimum, it indicates a serious insulation fault. The VCU then has to execute a precise response, from a major warning to an immediate shutdown.
And finally, that essential power-up sequence. Pre-charge logic.
This is non-negotiable for system health. The big capacitors in the inverter, when they're discharged, they act like sponges. If you just slam them with high voltage, you get a massive, destructive inrush current.
So you need to ease the power on.
Exactly. The VCU controls a precise timing sequence. It first closes a low-current pre-charge relay through a resistor. This slowly and safely charges the capacitors. Only after the VCU verifies the voltage has stabilized does it then close the main positive relay, allowing full power to flow. Getting this timing wrong means destroying components.
Okay, so based on these two architectures, what's the strategic recommendation, especially for a startup or a new team entering this space?
Based on our consulting experience, we advise a strategic starting point, the distributed domain architecture. Do not attempt a high integration 3-in-1 unit right out of the gate.
That's interesting. Integration, putting the VCU, motor controller, and DC-DC converter all in one box is the trend in high-end EVs to save space and wiring. Why recommend separating them for this segment?
It is purely a risk management and time-to-market decision. Trying to integrate the VCU and MCU functions into a single box requires expertise in both high-level control and high-current power electronics. The complexity is enormous, and the validation cycle for that combined piece of hardware is typically 18 months, which just kills time to market.
So you adopt the gray box approach, separating the complex systems. Can you break down the component roles in this topology?
Sure, we separate the brains from the muscles. The VCU is the true domain controller. It handles all decision-making, arbitration, energy, and thermal management. It's the brain.
And the motor controller?
The MCU, or motor controller, is purchased as a standard, mature, off-the-shelf unit from a Tier 1 supplier. It's dumb in terms of strategy. It just receives a precise torque command from the VCU via CAN.
Simple and reliable.
And the BMS remains integrated within the battery pack, dedicated solely to cell safety and communicating its limits to the VCU.
The major strategic benefit of this separation?
Supply chain flexibility. In the fast-moving micro-EV world, your motor supplier might change frequently. If the VCU and MCU were integrated, changing the motor requires redesigning the entire control box. With separation, if the motor changes, you only update the VCU's software, the CAN matrix, and the torque parameters. You keep your validated VCU hardware. It saves a fortune in redesign costs.
We've established the regulatory constraints in the optimal architecture. Now for the physical mandate, the hardware SOR. We have to balance these high safety standards with the very low BAM cost target of the segment.
And that's the core challenge. So for the microcontroller of the brain, it must meet automotive standards. We mandate a 32-bit automotive-grade MCU with the entire torque control path targeting ISO 26262 ASIL-C. That's a high bar.
So let's look at the options. You suggested two paths, balancing safety and cost.
Our first recommendation, favored for its cost-effectiveness and robust ecosystem, is the NXP S32K3 series. Specifically, models like the S32K312 or S32K314.
And why is this chip suitable for ASIL-C, which is a high integrity level?
It's based on the ARM Cortex-M7 architecture, but critically, it features lockstep cores. This means two independent cores run the exact same code in parallel and constantly cross-check their results. If the results diverge, the system knows a fault has occurred. This inherent redundancy supports the diagnostic coverage you need for ASIL-C.
And it has security built in.
Yes, it includes a built-in hardware security engine, or HSE, which future-proofs the platform for mandatory cybersecurity standards.
And what's the high-power gold standard option?
That would be the Infineon AURX TC3XX series. They use the specialized tri-core architecture. These chips are really the gold standard for complex powertrain systems. They have the raw computational power you need for running very complex torque models and thermal simulations. The trade-off is simply a higher unit cost.
Regardless of the MCU choice, there's a mandatory hardware requirement for future development, memory capacity for updates.
Absolutely. To future-proof the product and support modern software deployment, the flash capacity must be a minimum of 4 megabytes. This is essential to support robust AB, partitioned over-the-air, or OTA firmware updates.
So you can hold two versions of the software at once.
Exactly. You need space for the current verified operating system, Partition A, and the new downloaded update, Partition B, simultaneously. If the update fails, the VCU has to be able to boot back to the stable Partition A.
Let's talk about the I/O. The VCU is the nervous system, so defining the pins is critical. What kind of configuration handles the necessary complexity?
For this level, we recommend an 80 to 121 pin high-density connector configuration. On the analog input side, the safety-critical inputs are the accelerator pedal dual-path signals for that redundant cross-checking, and a dedicated brake pedal position input, which is essential for determining the precise depth of regenerative braking.
And what about the crucial digital inputs that flag immediate safety states?
Those include the instantaneous crash signal from the airbag controller, the status of the HVIL, either open or closed, and the charge wake-up signal to initiate charging logistics.
And on the output side, the VCU is driving those life-critical, high-voltage relays.
Yes, the VCU must have dedicated power output drivers for the main positive, main negative contactors, and the pre-charge relay. And the critical detail here is that these drivers must include current feedback diagnosis.
Why is that so important?
It allows the VCU software to verify that the relay actually closed when commanded. If the VCU commands the main relay closed but detects no current flow, it signals a relay sticking fault, which is a major safety concern.
Finally, the communication buses. What are the mandated networking standards?
Robust high-speed networking is mandatory. We mandate CAN-FD one flexible data rate for the powertrain domain connecting the VCU, MCU, and BMS. We insist on FD because the data volume required for future diagnostics will quickly outstrip standard CAN.
And for the rest of the vehicle?
CAN2 is reserved for the body and chassis components, the cluster, ABS, EPS, and T-box. And then LIN is used for simple, low-cost peripherals like cooling valves or wipers.
Now, you emphasized this earlier, but it's worth repeating. Connectors are a huge failure point.
We have to emphasize this point. Based on field returns, connector failure is the single top fault mode in LSEVs. Choosing cheap industrial connectors is a guarantee of field failures and warranty claims. Industrial D-sub connectors are absolutely forbidden.
So we need solutions that can handle the massive vibration and environmental exposure. Which specific connectors are required?
We mandate highly reliable sealed automotive solutions like the TAD AMP Seal or Molex MX150 series. They achieve an IP67 waterproof rating, but their key feature is the Connector Position Assurance or CPA mechanism. It's a secondary locking latch that ensures the connector cannot loosen over time from vibration.
The housing design also has to handle massive thermal swings and, well, user abuse.
Correct. The housing must be die-cast aluminum to facilitate passive heat dissipation. And here is a frequently overlooked detail. It must incorporate a breather vent.
A breather vent? Isn't that counterintuitive for a waterproof seal?
It's essential physics. Without a vent, rapid temperature changes, like driving a hot vehicle through a puddle, cause the internal air pressure to drop. This negative pressure can actually siphon water right past the seals. The breather vent balances the pressure while using a hydrophobic membrane to maintain the IP rating.
And the final required ingress protection rating.
Given that users often clean these vehicles with high-pressure water, the VCU has to achieve IP67 and IP6K9K. That latter rating certifies resistance to high-pressure, high-temperature steam spray. It's a baseline for true reliability in this market.
So it's one thing to design the component, but another to prove it will survive its expected life. This requires passing the rigorous ISO 16750 environmental validation standards.
These tests are brutal, but they are absolutely necessary. Let's start with electrical load testing, ISO 16750-2, which simulates real-world electrical abuse.
The first common scenario is just user error during maintenance, right?
Exactly, that's the jumpstart test. The VCU must survive 24 volts applied for 60 seconds. This simulates the very common, very dangerous error of a user mistakenly connecting a 24-volt truck battery for a jumpstart. A non-automotive component would be toast.
And the test that protects the component from system anomalies, the infamous load dump.
Load dump, or Pulse 5B. This test simulates the extreme voltage spike that occurs when the battery is suddenly disconnected while the vehicle's charging system is still operational. The VCU must contain internal circuitry, usually TVS diodes, to absorb that spike without damage. We also mandate passing reverse polarity testing.
Just in case someone connects the battery backward.
It happens. The VCU can't be damaged by it. And finally, mechanical durability. ISO 16750 ZAS3, which focuses on vibration.
The constant enemy.
It is. We mandate random vibration testing, which is mathematically superior because it simulates the complex varying frequencies of a real road, unlike simple sine wave testing. And the required intensity level test C for body-mounted or test 6 if mounted directly to the frame is critical. You have to define it based on the VCU's final mounting location.
We've specified robust hardware that can survive the world. Now we turn to the software, the core intellectual property that determines the vehicle's performance, safety, and efficiency. We are moving decisively away from the legacy bare metal code.
This transition is where a startup either succeeds in scalability or fails in complexity. Bare metal programming is just unsustainable for high safety applications. The mandate is crystal clear. Adopt a layered architecture.
And that means adopting AUTOSAR Classic. Why is that mandatory for this platform, even with the steep learning curve it implies for a new team?
AUTOSAR is essential because it's the industry standard for standardization, modularity, and scaling. Think of it as the Windows or Linux for embedded automotive systems. It forces software to be developed in reusable, independent components, which dramatically reduces long-term development costs and risk.
So let's break down the required layers of this architecture.
At the bottom, you have the basic software layer, or BSW. This has the operating system, the hardware drivers, the communication stack, the memory stack. It's all the infrastructure. And as a consulting mandate, we strongly advise the team to purchase licensed, mature BSW solutions from vendors like Vector or EASS. Do not build this in-house.
Why the hard line on buying the BSW?
Engineering resources are scarce and expensive. If you try to build your own BSW, you will spend years debugging low-level hardware drivers work that adds zero competitive value. Buying the BSW frees your highly skilled engineers to focus exclusively on the next layer.
Which is connected via the runtime environment, or RTE.
Yes. The RTE is the standardized interface, the messaging service that connects the application layer to the BSW. It ensures the control algorithms don't need to know or care about the underlying hardware.
And finally, the true competitive edge, the application layer, the ASW.
This is the part you must develop in-house. The ASW is where the team's IP resides, the bespoke torque control models, the sophisticated energy management strategies. This layer is often best developed using model-based design tools like Simulink, which allows for really rapid iteration and validation.
Let's talk about the VCU's most complex role, torque management and arbitration. Before we get to the arbitration, let's define the base driver input, the pedal map.
Right, we need a nuanced, nonlinear curve for the accelerator pedal. At low speeds, say below 10 km, you want significantly reduced sensitivity. This prevents jerky starts and allows for precise control in parking.
And then it ramps up.
As speed increases, the VCU should ramp up responsiveness to give the driver that peppy feel that defines a good EV experience in the mid-speed range.
Now for the complexity, the arbitration hierarchy. The VCU might get a driver request for 100% torque, but the BMS says the battery's too cold and the ABS system just kicked in. Who wins?
Safety always wins. The VCU has to operate based on a strict 4-level hierarchy of priority.
Level 1, the immediate safety override.
Safety interventions. This is paramount. A crash signal, activation of ESP or ABS, or a critical ASIL-C fault must instantly result in torque zeroing or active reduction. The motor obeys the safety system before the driver.
Level 2, protecting the hardware.
System limits. This manages component boundaries. If the BMS reports a discharge current limit or the motor is overheating, the VCU must enforce a maximum torque restriction to prevent permanent damage. It's a derating function.
Level 3, legal and operational boundaries.
Vehicle limits. This includes the mandatory speed limits, 45 kilometers for L6E, or the fixed reverse speed limit. These are managed via a precise PID closed-loop control system.
And finally, the lowest priority, the driver's request.
Driver demand. Only if all 3 higher-level constraints are satisfied is the VCU allowed to deliver the base torque requested by the pedal. This meticulous arbitration sequence is the heart of VCU functional safety.
We mentioned the need for an anti-rollback function earlier due to the lack of a mechanical P-gear in this segment.
Yeah.
How does the software execute that smoothly?
It relies on high-fidelity sensor input, specifically an integrated accelerometer. The VCU uses it to determine the precise slope of the road. When the driver releases the brake but hasn't yet touched the accelerator, the VCU has to recognize it's on a slope and automatically output small, calculated holding torque to prevent rollback.
And then it has to transition smoothly to driving.
Yes, it monitors the accelerator input and smoothly transitions from that holding torque to the desired drive torque without any perceptible jerk or delay.
Safety also means managing thermal limits and providing a plan for system failure or low power. This is the limp home matrix.
The VCU must manage graduated safety tiers. Level 1 is a warning. If the state of charge drops below 15% or there's slight overheating, the VCU enters an advisory state. It restricts top speed to 25 km, limits acceleration, and shuts off non-essentials like AC cooling.
So the driver has mobility but is conserving energy.
Exactly. Then you have level 2, the critical fault state, or turtle mode. This is the emergency protocol. If SOC is below 5% or there's severe overheating, the VCU severely restricts speed down to a crawl, maybe 10 km maximum. The purpose is just to allow the driver to safely pull the vehicle off the road.
Thermal management also requires managing cooling loops. You specified the use of hysteresis control for fans and pumps. Why not just simple on-off control?
Simple on-off control causes components to cycle rapidly. If you set the motor to cool at 85 degrees, the fan turns on at 85.01, cools it to 84.99, turns off, and then immediately turns back on. This rapid cycling causes excessive wear on fans and pumps and creates current spikes.
So hysteresis control creates a lag.
It creates a lag, a band. If the motor heats up to 85 degrees C, the VCU commands the fan to 50% PWM. But the VCU won't turn the fan off until the temperature drops to a lower predetermined threshold, say 80 degrees C. This hysteresis band prevents the components from constantly switching on and off, which extends their lifespan.
And finally, connecting back to the GB standards, the VCU's role in cold weather charging.
The low-temperature charging preheating function is crucial for lithium battery health. If the VCU reads a low battery temp on plug-in, it has to prioritize thermal recovery. It activates the PTC heater to warm the battery before closing the main contactor for fast charging. Only once the battery has recovered to a safe temperature does it allow the high current of the fast charger to flow.
Let's talk regenerative braking. It's key to efficiency, but requires millisecond coordination with the friction brakes.
Absolutely. So for single pedal driving, lifting the accelerator generates negative torque. The VCU has to precisely calculate this regen amount. The calculation is dynamic, based on speed, but it's strictly limited by the charge current limit, or CCL, a signal sent continuously from the BMS. You can't exceed the CCL.
And the ultimate safety test for regen is coordination with the ABS system. What must the VCU do if ABS activates during regen?
This is a life-critical safety function. If the VCU receives an ABS activation signal, indicating a potential wheel lockup, it means the hydraulic system is fighting for traction. The VCU must immediately cease all regenerative braking torque. This cutoff has to happen within a non-negotiable time frame of 10 milliseconds. Any delay interferes with the hydraulic system's ability to modulate pressure.
So to function as a modern, globally serviceable vehicle, the VCU must speak the language of diagnostics, UDS, based on ISO 14229.
Correct. UDS server functionality is mandatory for EOL configuration, calibration, and aftermarket service. It standardizes the technician interface globally.
Which core UDS service IDs are required for this VCU?
You need several. 0x10, session control, to switch diagnostic modes. 0x19, read DTC, for pulling diagnostic trouble codes essential for fault diagnosis.
And crucially, the security layer to prevent unauthorized manipulation.
That requires 0x27, security access. This uses a seed and key mechanism. The VCU presents a unique seed number, and the diagnostic tool must perform a cryptographic calculation to return the correct key. Without the correct key, the VCU denies access to sensitive functions like flashing new firmware or modifying speed limits.
And supporting over-the-air updates requires specific data transfer protocols.
Yes. Services 0x34, 0x36, and 0x37 are required to manage the block transfer of the firmware image during OTA updates. And underpinning all of this is the requirement for secure boot. The VCU's bootloader must verify the cryptographic signature of the firmware at startup, ensuring only factory-signed, authenticated firmware can ever execute.
We've defined the architecture and the software IP. Our final phase addresses safety proof and economic viability, the two factors that turn a prototype into a mass-market, profitable product.
Right. Functional safety is the proof of compliance. We have to formally assign automotive safety integrity levels, or ASILs, to all critical functions based on risk analysis.
Let's confirm the key ASIL assignments for the Micro EV VCU.
The highest safety level is required for the torque control path. We target ASIL C. The hazard unintended acceleration is a catastrophic risk, demanding the highest integrity. Regenerative braking control often targets ASIL B. And thermal management monitoring, which primarily affects durability, targets ASIL A.
How do you physically achieve ASIL C integrity on the MCU beyond just using lockstep cores?
We use the established three-level monitoring architecture, also known as the e-gas concept. This involves 3 independent layers of oversight to ensure no single fault can cause unsafe operation.
Can you describe those 3 layers for us?
Sure. Level 1 is the functional layer. This is the primary core running the complex torque calculation. Level 2 is the monitoring layer. This runs on a separate core and uses a different simplified algorithm to continuously recalculate the safe torque limit. It acts as a referee.
So it's checking the work of the first level.
Constantly. If the output from level 1 deviates excessively from the safe limit calculated by level 2, the monitoring layer immediately cuts the output torque. And level 3 is the hardware layer. This is the ultimate fallback, using external watchdog timers and continuous hardware RAM checks to make sure the MCU itself hasn't frozen or corrupted its memory.
Moving from concept to reality requires a rigorous design verification plan, or DVP. You strongly advocate for the model-based design flow.
MBD is the only way to meet competitive timelines. We proceed through model-in-loop and software-in-loop testing to verify the logic. But the most important and non-negotiable validation stage is hardware-in-loop, or HIL testing.
And why is HL mandatory for this VCU?
HIL testing connects the actual physical VCU to a real-time simulator. This lets engineers safely test catastrophic, highly dangerous failure scenarios in a lab, bypassing the need for thousands of road tests and avoiding destroying vehicles.
Can you give us an example of a dangerous scenario that only HIL can safely test?
We test faults like a simulated short circuit to power on the accelerator pedal signal, a guaranteed unintended acceleration, or main contactor weld shut at high speed, or CAN bus disconnection. The HIL system injects these faults thousands of times to prove that the ASALSUM safety mechanisms always detect the fault and degrade the system into a safe state.
Let's review the final physical tests mandated in our DVPNR matrix.
The matrix must include all physical abuse scenarios. Electrically, we verify load dump, the 24V jumpstart, and reverse polarity survival. Environmentally, the VCU must survive thermal shock cycling rapidly between -40°C and +85°C for at least 100 cycles, and a rigorous 96-hour salt spray test to verify corrosion resistance. And functionally, the HIL fault injection testing validates the safety compliance.
Now for the economics. For a cost-sensitive micro-EV platform, we have to achieve this high level of safety and reliability while hitting brutal cost targets. This requires a precise make-or-buy decision.
And we recommend the gray box model for any new team, unless their annual volume already exceeds 100,000 units. Custom hardware is just a time and money sink.
So, strategically, what do we buy?
Buy the hardware and the basic software. Purchase existing, validated VCU hardware from established Tier 1s like Bosch or Vitesco. Likewise, purchase the licensed AUTOSAR BSW toolchain. This avoids the 18-month hardware validation cycle.
And what must be developed internally, where the competitive value lies?
Make the application software. The core IP is the proprietary control model, the torque management algorithms, the unique acceleration profiles, the advanced energy management. This is what defines the vehicle's driving feel and achieves the mandatory energy consumption figures. This is where the team focuses its talent.
Finally, the critical economic constraint. What is the target procurement price for this advanced, globally compliant VCU?
For the LSEV segment, the target procurement price has to be fiercely controlled. It needs to fall between $80 and $120 USD. Missing this price point makes the final vehicle unprofitable.
That is astonishingly low for an ASIL-C domain controller with this level of complexity. What are the highest cost contributors within that tight budget?
The analysis shows that the safety-rated microcontroller unit accounts for about 20% of the cost. But the surprising second largest contributor is the housing and connectors, which can be about 25%. This cost is directly driven by the requirements we discussed. The need for expensive die-cast aluminum for thermal performance, and those mandated high reliability IP6K9K rated connectors to prevent field failures. Quality enclosures and connectors are non-negotiable safety expenses.
This has been an incredibly detailed look into what it takes to engineer a modern micro-EV, revealing that this segment, often dismissed as basic, faces some of the most complex engineering challenges due to regulatory divergence and ruthless cost constraints.
We've established that the micro-EV VCU is no longer a rudimentary switch. It's a sophisticated powertrain domain controller, driven by the necessity of global type approval. Our SRR framework mandates balancing EU anti-tampering logic with US downhill speed control, satisfying China's zero-fire safety prerequisites via low-power monitoring, and integrating Japanese driver assistance technology.
The resulting solution requires ASIL-C hardware utilizing lockstep cores, a mandatory transition to the AUTOSAR layered software stack, and proving compliance through rigorous ISO 16750 electrical and environmental durability testing.
So what does this all mean for the future of urban mobility? Well, implementing this stringent SOR framework fundamentally elevates the entire MEV market. It creates essential technical barriers that filter out low-quality manufacturers, ensures product compliance and passenger safety, and establishes brand credibility. It transforms these products from high-risk golf cart controllers into safe, modern, globally marketable technology platforms.
We spent considerable time on the VCU's new role as a perpetual guardian, specifically through that mandatory low-power monitoring mode required by China's GB standards, a state where the VCU must constantly listen for signals from the BMS even when the vehicle is off.
Indeed. It raises a provocative final thought for you to consider, one that defines the future of all EV architecture. How does the increasing reliance on low-power VCU safety systems, which must be perpetually active, capable of sounding alarms and transmitting data, fundamentally change the very definition of power off in a modern EV. Is the VCU now a silent, continuous guardian, making the vehicle less a machine that turns off and more a continuously networked, always-on safety device?
Food for thought indeed. Thank you for joining us for this deep dive into the future of micro EV control systems. We'll see you next time.